Oh my gosh.
Hi, Professor. Good afternoon.
Hey, how are you?
I'm pretty good. How about yourself?
Good.
Awesome.
All right, we're going to do 2 sections today. 8182.
We're gonna do which sections?
8182.
I don't think we've done 4.5 yet.
4.5 is the application part of the of section 4. So
Oh, okay. Like word problems.
yeah, we can go through a few after we're finished.
Okay.
So we have a few minutes till we could get started. So I'm going to just wait for everybody to get here. Should be ready to roll in a few minutes. Oh goodness, this girl's ready to fall asleep. It's just a Coco. Let's see if I can find linear. Let's see if I can find this is a nice one. And not what I'm looking for, thanks. Ah, yes. Whatever. All right, if I have you here on this call, I'm going to actually start with a little bit of background information on this concept, which we're due 8182. It's basically they're related concepts. If you're paying attention here, one of the things I want to bring to your awareness is the use of this math that you're doing in this particular example. So I have for you here a linear programming example from a book, one of the books where I teach. And we cover a question that's very popular among linear algebra teachers, and that is the bull versus mug example. And in essence, what it is, it's an example of how this concept you're learning here, or at least the foundation of it, how it's related to this. So if you look down here, you have either two products that you're making. You're either making bowls or you're making mugs. But you have what we call parameters or constraints, which are resource requirements. And that is, for example, that you only have 40 hours total of labor available. And you also have a certain amount of clay available. And you also have profit. And so we are able to put this into literally a math model where we would turn this into, just like you see that now, if you notice they use x1, x2, their x2 is the equivalent of our y. And so you can see the model constraints for x and y, for the labor, and for the materials. And eventually you end up with this inequality. All right. And so when businesses are looking at what the optimal operational function of their company should be based on decision variables, which is exactly what this is tying back to, this is what it looks like. So imagine if I translated this where x2 was a y, now we're back to our typical equation. So I just wanted you to see that what you're learning does tie into management, and eventually it does come together and it leads us to optimization points. Now, what's really cool is there is a program, and I'm going to share with you the program. I have it on my screen because I'm actually tutoring someone at FIU, or was it FAU, for one of the F schools. Then they're actually taking this class. And this is called POMQM. This is a program that actually does decision analysis. And this is what's called a decision table. So in a decision table, if I have two decisions, two nature of states, I would set it up. And, if I have probabilities or if whatever it is that I have in terms of information, whether it be a cost equation or profit equation, I would state the conditions, and then I would run the model. And the model that this would actually spit out, let me see if I happen to have a picture of it. Let me see if this page happens to have it. Yeah, this is a graphical solution, so maybe this one has the actual picture. Okay. So if you notice, this does show the X and Y axis. And what it'll do is it'll start to graph these. You see the little blue line, that's one of them, that's the other. And then this is our solution area at the moment. And eventually we find what's called the optimization point. You find it here once you figure out where the overlap is, and then you select your optimization point. So notice they call it the optimal solution in this case. So which value of x1, which is your number of hours, which value of x2, which is your amount of labor available, would produce you the highest function profit, which in this case would be your 800. So all of this is tied right back to your lesson, FYI. So kind of cool stuff. I just wanted to bring that to your attention, just so you know that you're not just doing this for the sake of, some sort of exercise in math. Yes, it's an exercise. Yes, you're learning this from the ground up, but understand that there's a further connection to that in some of the math and decisions you make in business and whatnot. All right, with that said, we're covering two sections today. We're going to cover section 8.1 and section 8.2. They are extremely related. In other words, there's not much difference in them. And so let me start with 8.1. And we're going to cover some questions in 8 and 4 or 5 time permitting, but they're just word questions relating to your previous lesson. Any questions? I hope you guys are well. I know that we're under hurricane or tornado warning here in this area here in Pembroke. I don't know about you guys. All right, let me take myself off camera, preserve my battery, and here we go. So I think 8.1 will be fairly easy for the majority of you. 8.1 begins with, in this case, we're looking at systems.
We don't see your screen, Professor.
If I had $1 for every time I did that. Okay, you see it now?
Yes, and I think you probably have $7.
I'm more than that. I'm telling you, I'm filthy rich. Okay, systems of linear equations in 2 variables. Now, the only difference between 8.1 and 8.2 is in 8.2, we start to do 3 variables, 4 variables. So we're going to begin with just systems of linear equations in 2 variables. That's going to be our first one. In this section, there's only 8 examples. The first example is extremely easy. And basically, they give us a system, and the key is determining whether an ordered pair is a solution of the system. Now, keep in mind that for it to be a solution of the system, it has to work and be a solution to both of the equations, not just one. It has to work for both. All right, so they give us the first system, and they give us x plus 2y equals 2, and x minus 2y equals 6. And then they give us 2 coordinate points to test. So the first coordinate point is the coordinate point 4, -1. And so we begin by plugging in the values. Remember, this is x, this is y. So if we start with the first one, we have 4 plus 2 times -1, which ends up giving us 2. So that checks out. That is a solution. Keep in mind, I'm merely substituting in those 2 values into the equation respectively. The second equation, now for it to be a solution of the system, it has to work for this one also. So here I end up with 4 minus 2 times -1, and that should equal 6, and that is also true. Again, I'm substituting in these values to obtain the value of 6, which is true. So we would say that in this case, because it works for both, this is a solution for the system. It has to work for both. That is the key. Now, if I give you a second example, and for part B, they're asking me to check the coordinate pair -4, 3, and using the same system. So in this case, -4 plus 2 times 3, does that equal 2? And the answer is yes, because 6 minus 4 is 2. We're good. So that does check out. However, if I plug in -4 minus 2 times 3, my answer in this case is equal to -10. This does not match that solution. So this is not a solution for the system. Okay, is that easy enough to remember? It has to work for both to be a solution of the system. Are we good?
Yep.
Cool. I'm going to go to the next question. Example, I mean. This is example 2. In example 2, we are simply solving the system. We actually want to know what the solutions are. Now, specifically, they want you to solve the system by substitution. You will know that they're asking you to solve it by substitution because as they give you the system, as in this case, 5x minus 4y equals 9, and you have x minus 2y equals -3, you'll notice that there's a single variable by itself. And I can simply take this particular sentence right here, and I can re-express this as x equals 2y minus 3. What I would then do is take this x, and instead of saying 5x, I would say 5 parentheses 2y minus 3, which is the equivalent of x, minus 4y equals 9. If I distribute, notice that I get 10y minus 15 minus 4y equals 9. And when I collect the like terms, I end up in this case with 6y minus 15 equal to 9. I'll add the 15 to both sides. This leaves me with 6y is equal to 24. And in this case, y is equal to 4. If that's the case, I could simply come back here to solve for x, where x is equal to 2 times 4 minus 3. And that gives me x is equal to 5. So my solution for this would be 5, 4. Done. That's what they want with respect to substitution. Is that easy enough, or do you need another example?
Professor, quick question. When you, on the first part where you set x equals to 2y minus 3, why didn't you bring the negative as well?
I'm moving the 2y, so I have to subtract it on both sides. Right?
Oh, okay.
A minus minus 2y becomes a plus 2y plus 2y. So this is plus 2y minus 3.
Okay, I just wanted to, I wasn't getting that. Thanks.
You want another one?
Why not?
Okay, let's do another one. So go ahead and solve for this one using substitution, where I'm giving you, in this case, 3x plus 2y is equal to 4, and 2x plus y is equal to 1. Okay, if you remember, for those of you struggling, remember that I'm going to, in this case, subtract the 2x on both sides. So this all becomes y equals negative 2x plus 1. In this case, because I solved for y, I'm going to substitute this in here. So you have 3x plus 2 times negative 2x plus 1 equal to 4. This is going to give me 3x minus 4x plus 2 equal to 4. This is going to give me negative x is equal to 2. So therefore x is equal to -2. And if I plug this back in here, then that means that y is equal to -2 times -2 plus 1. So y is going to equal 5. My solution set for this one is going to be -2, 5. All right, are we cooking with fire?
Yeah, that was pretty decent.
All right, cool. Any questions, any issues? No? Okay. Can always stop me. We can always talk. Don't ever be shy or hesitant to ask a question. Okay, this one is also solving a system. But this time we're not going to use substitution. We're going to use the addition method. All that means is that I don't have a single variable, but I have two variables or one variable that I can build up. So let me show you what I mean. I'm going to start you with 3x plus 2y is equal to 48. Here I have 9x minus 8y equal to -24. So choose a variable you want to cancel. I always tend to be a little on the I don't know if it's lazy or slick, but you see how this is already plus minus? I could just build this up by multiplying by 4. And they would cancel. So if I took this entire, just the top part, and I multiplied it by 4, this will become 12x plus 8y is equal to 48 times 4, which is a number that I am battling right now to think of. I want to say 72. No, it can't be 72. 172. Anybody with a calculator want to verify? I want to say 192.
Yeah, it's 192.
Awesome. So this is 192. All right, and that's because I decided to focus on the y values. So when I put these together, that means that the 8y and the -8y are going to immediately cancel. That's what I want. This gives me 21x is equal to 192 minus 24, which should be 168. And if that's the case, I'm going to now divide 168 by 21. What is 168 divided by 21? My x is 8, right? So now that you know x is 8, what you'd want to do is go back to your original problem. We had a 3x plus 2y is equal to 48. And now that we know x is 8, that means that 3 times 8 plus 2y equals 48. Now here's what we do know. This is 24, which I'm going to subtract on both sides. That leaves me with 2y is equal to, again, 24. So that means that our y value has to be 12. My solution set would be 8, 12.
If we wanted to, can we use the 9x?
Yep.
Okay, that's
Sure.
my question.
Well, what I was saying was I was trying to be slick by using the plus minus that's already here, you know? But okay, just to play devil's advocate, let's do the top one. Let's do the x. Now it is doable. And the reason why this is a good choice as well is that you're going to focus here by multiplying by -3 all across all of it. You want a negative 3 because you need a negative 9x. Negative 3 times 2y, that's minus 6y, and that's equal to 3 times, or negative 3 times 48. That gives us negative 144. Do you see what I'm saying? Now that cancels. The x's will cancel. You're left with negative 14y is equal to negative 144 and negative 24. That's going to be negative 168. You're going to then divide by negative 14 on both sides. And guess what you get? Y is equal to positive 12, because negative divided by negative is a positive. Now you would go back again. You would say then 3x plus 2y equals 48. Since we know y is 12, we have 3x plus 24 is 48. We are going to subtract that 24 on both sides. And that leaves us 3x is equal to 24. And therefore x is equal to 8. So either one would have worked. Would you like to try one more of those? Or move on?
I can move on. I actually did this last semester.
Cool. Yeah, all of you should have, actually.
Yeah. Isn't that complicated? It's just refreshing the memory.
Yeah, I know for a fact we didn't do more than 2 variables though.
Oh yeah, we're going to do 3
Mhm.
and 4. All right, so move forward. This is example 2, or example 4. Now, this is the only thing with this one, it's the same process. We could go ahead and do it anyway. For those who have never taken this in algebra, which I doubt that you'd be in this class. So if you notice, this is all out of order, right? It's all over the place. So the first thing you'd want to do is have it so that you would have x plus or minus some y equal to some number. Have you noticed I already started giving you a hint? So I'm going to reorder the first one because I'm going to subtract the 7y. I'm going to get 7x minus 7y. 2x minus 7y equals negative 17. On this side, I'm adding the 3x. So I have 3x plus 5y equals positive 17. Now, I'll tell you, you're going to follow the same process here. The only problem is this time you have to build both. Build both. What I mean by that is, if I'm looking at the x's, I'm going to consider getting rid of the x first. So that means that I have to multiply maybe this by negative 3 and this by positive 2. That's what I mean by build both. If you do that, I went with negative 3 at the top, right? So that's going to give me negative 6x plus 21y is equal to positive 51. In the bottom, I have 6x plus 10y equals negative 34. I mean, positive 34, the opposite. If you add these up together, you're going to get positive 31y is equal to positive 85. And notice that you're going to get a very ugly number. We get y equals that nasty fraction. My suggestion is don't substitute it back in. Don't do that. Just take the originals and now let's focus on the y term and canceling that out. So we start with 2x minus 7y equals negative 17. And we have a 3x plus 5y equals positive 17. So if I focus on the y terms, I'm going to multiply the top by 5, and I'm going to multiply the bottom by 7. Notice that I'm not changing the signs because this will give me a negative 35y, this will give me a positive 35y, so the y's are going to cancel no matter what. Now I could just focus on the x values. So I'm going to get 10x minus 35y equal to negative 85. And if I distribute the 7, I'm going to get 21x plus 35y is equal to 119. Again, the 35y's cancel. Look at how ugly the numbers are. You get 31x equals 34. And so therefore x is equal to some nasty little fraction called 34 over 31. Notice that I got the answers respectively, and that is your answer. But it defeats, it eliminates you having to go through the nightmare of multiplying those if you substitute them. Okay, so that's my suggestion, my 10 cents, take it or leave it. I say it's a very good 10 cents to keep.
Way better than plugging back in.
Oh yeah, oh yeah. Do you want to try one of those?
I'm good
Fine,
personally.
honestly.
Huh? I heard a second voice, or are you good or not?
I said that I'm fine in my
Oh, you're
case.
fine, okay. Okay, then moving on of this example. So I guess the point of that one is if you hit a nasty fraction for an answer, don't plug it back in, just solve the other variable. Okay, so there's two systems, and this is examples 5 and 6. Let me just make sure that's also 6, yeah. So this is a no solution, a system with no solution. This is a system with infinitely many solutions. If you remember, this is the straight line versus the parallel line, where this is the one that's parallel lines, no solution, and this one is the same line over itself. So it has infinitely many solutions. In this prior system we've been doing, there's only one solution. This is the one where you have an actual value that's shared. That's why you get the xy. Okay. So with a no solution, what you're looking for is you get an irrational answer. For example, if I have 4x plus 6y and this equals 12, and I have 6x plus 9y and this equals 12. If I multiply the top, hypothetically, to cancel out the x's by 3, let's go with 3, and then multiply the bottom by -2, I'm going to end up with, if I do this one first, positive 12x plus 18y equal to 36. And this next solution here is going to be negative 12x minus 18y. Do you already see a problem? Is equal to negative 24.
They both cancel.
They both cancel, leaving you a 0 is equal to 12 in what planet? So when you see no solution, look for this as your answer, something that doesn't make sense. All right, so we will say that this is a null set or there is no solution. It's inconsistent. It's a false statement. You can always think that way. This will always give you a false statement because they should never overlap. You know, think of a train track, think of a road, think of, you know, anything that has to have that parallel aspect. It should never cross. So yes, this would make sense for it, which means null set. Now, if it's infinitely many solutions, you'd have a system like this next example. This next example starts with negative 3x plus y is equal to negative 2. And then here I have 15x minus 5y is equal to 10. So guess what I'm going to do to the top? I'm going to multiply it by 5. And guess what this is going to become? Negative 15x minus 5, or actually plus 5y is equal to, in this case, positive negative 10. So the x's cancel, the y's cancel, the answers cancel. You get 0 is equal to 0. I mean, if you left the answer, you would still also get 10 is equal to 10 if you substituted. Point is, even though this looks kind of strange, it is a true statement. It's not false. So in these kinds of answers, you're looking for something like 10 is equal to 10. Had we used substitution, we would have gotten 10 is equal to 10. Or 6 is equal to 6. Something that makes sense. It's rational. It's a true statement, even though for us, like we're like shaking our heads to a point. All right. Are you cool with that so far?
Yeah.
Yep.
And it's the same process you're still trying to solve. Okay. Example 7. Example 7 goes back to the business model that I was talking about. More specifically, this is asking for a break-even point. So we start with a couple of definitions. So please pay attention to this part because you might have forgotten it. We have the revenue function. We have a cost function. We have a profit function. And all of these are part of the same lesson. So the revenue function is basically referred to as the RX, which is the price per item sold. The cost function is equal to the fixed cost plus the cost per item produced. So if I make, 10 t-shirts and it costs me $5 per t-shirt, I've still got a cost, right? So however many t-shirts I make, multiply that times a -5 in a sense. Then I also have a profit function. And my profit function in this case is going to be the P of X, which is equal to the revenue function minus the cost function. And that's the profit function. So here's where they start us with the question. Okay, and I'll go ahead and type it up so you can see it clearly and get. Okay. So in the question, it starts with the wheelchair company. So they give you a bunch of backgrounds. So they start with technology is now promising. Bring light, fast. Beautiful wheelchairs. to millions of people with disabilities. It says a company is planning to manufacture these radically different wheelchairs it says fixed cost will be 500,000 and it will cost 400 to produce each wheelchair. Each wheelchair will be sold for $600. So in part A, they want you to write the cost function. In part B, they want you to write the revenue function. In part C, they want the break-even point. Let me give you a minute to try to do that and see if you can put it together. And give me 5 seconds to step away for a second and get something at the door. Okay, how did we manage on this?
I think I did A and B, but I didn't get right the break-even point.
You don't think you got the break-even point?
No, I didn't get to write it.
Okay. So let's start with A. They want the cost function. So the C of X in our case, which actually would be the 500,000 plus the $400 times however many chairs they make, we'll call it X. We know that the revenue function, R of X, that has to be, in this case, 600, because that's how much profit they're going to make per chair. And the break-even point, you simply take the 600X and set it equal to the 500,000 plus the 400X. And let's solve for X. So if I subtract the 400X on both sides, that leaves me 200X is equal to 500,000, which if I divide by 200 on both sides, it tells me that I need to make about 2,500 chairs for that to happen, for it to break even. That's why you set them equal to each other. That is the break-even point in these examples. When you look at the graph, if I were looking at and look at this in terms of X and Y, I would have, let's say hypothetically, I had my cost function going this way. Let's say that's my cost. And let's say my revenue function is going to go this way. And they would crisscross somewhere here. This is what I'm looking for. That's the 2,500. That means that I need to make 2,500 chairs to make it to pass my fixed cost and then eventually make profit. So when you look at the big picture, the profit stems up here. That's all profit. You're losing money at the beginning because obviously you have costs and you have no money coming in, or very little money coming in. Here, that break even, you're at zero, ground zero, if you think of it that way. Does that make sense to you now?
Yes.
Whenever you see break even as a question, it's usually where are they equal to each other?
Basically equals 0, no?
Basically where they crisscross.
Okay.
Yeah. All right. Is everybody cool with that one? Yeah? No?
Yeah.
All right, cool. Now the next question is the mixture question. And in the mixture question, we have the following. So this is example 8, by the way. Okay, wait 1 second. Let me get the writing so it's legible. All right. So this is example 8, the mixture problem. This always tends to be a hot spot for students, so let's make sure we leave here knowing what you're doing. So here's your question. It says a chemist is working on a flu vaccine and needs to mix a 10% sodium iodide solution with a 60% sodium iodine solution to obtain to obtain 50 milliliters of a 30% sodium iodine solution. Their question is how many milliliters of the 10% solution and of the 60% solution should be mixed. That's the question. So you need a minute to write it down. Go ahead. I'm going to go ahead and get started in a second. So when doing this question, I would always decide which is X, which is Y. That's going to be my Y. This is going to be my X. So X is my 10% solution. And Y is going to be my 60% solution. So I know that I have two things I have to consider. One of them is when these two come together, I need 50 milliliters of a 30% solution. So I know that that X plus Y, amount-wise, has to equal 50. This is the amount solution. That's my how much. Now I look at the percentages and I'm thinking, well, I have 0.1x plus 0.6y. Well, that has to equal 0.30 because I will need a 30% solution right here of the 50 liters, which is what this is, which if I do the math, all of this is really equal to 15. And now at this point, I have a system of equations because I have the X plus Y equal to 50. That's my amount solution. And my percentages are 0.1x plus 0.6y. And that should total 15. So I could use substitution or I could build up and cancel. It's up to you. I would simply just take this equation, solve for X or Y depending. If I say X equals, then this is going to be 50 minus Y. If I say Y equals, then this will be 50 minus X. Whichever one you decide to use, just remember you're going to substitute it into respectively either one of those. So let's go with the Y equals 50 minus X. So I have 0.1x plus 0.6 times 50 minus X, right? Because I'm substituting in the Y. And this has to total 15 because that's the original equation. All right, so I end up with 0.1x plus 30, which is the product here, minus 0.6x is equal to my 15. If I add these two terms together, I end up with negative 0.5x plus 30 equals 15. Subtract the 30 on both sides. You're left with negative 0.5x is equal to negative 15. And now we're going to divide by negative 0.5 on both sides. And therefore x is equal to 30. But remember, if x is equal to 30, that means that my y has to equal 20. So I need 30 milliliters of the 10% solution and 20 milliliters of the 60% solution to get the 30% that I need equivalent when I mix both? And that's the question.
I remember doing this, but not on. Yeah, I remember doing this, but a little different, I guess.
It's the same thing. You can just do the X column, the Y column, and the solution column, and do it like this. So we already know that we have X and Y, and this has to be 50. That's where we get this from. And we know that this is 0.1X, this is 0.6Y, and this has to be 0.3 of the 50% or 50 milliliters. And that's where you get these two equations, that one and that one respectively.
Got it.
All right. Now we're going to look at the same concept in 8.2. The only difference is now we have 3 variables, X, Y, and Z. So as a manager, you're looking at maybe you have a union, so you have labor, you might have product cost, and you also might have salary caps. So the X, Y, Z could be any 3 variables. Just remember that in this case, in 8.2, when we talk about these systems of equations with multiple variables, that these are all decisions. Okay, so I'm going to start with example 1 of 8.2, which is basically linear systems and more than 2 variables. So example 1 is exactly like example 1 in 8.1, where I did is the ordered triplet, is what we call this. Is the ordered triplet or triple a solution? So they're giving you -1, 2, and -2 is a solution of the system. The system they're going to give you in this case is X plus 2Y minus 3Z equal to 9, 2X minus Y plus 2Z equal to -8, and -X plus 3Y minus 4Z equals to 15. It has to work for all 3. My suggestion, here's your -1, that goes in for all of these X's. Here's your 2, this goes in for all of the Y values. And here's your Z, which is your -2. And you plug that in for all the Z values. When you solve for these, so I'm just not going to waste your time. You just know to substitute them, right? So this will be -1 plus 2 times 2 minus 3 times -2. Does that equal 9? Yes or no is the question. So this is a true. You do it again with the next one. So you have 2 times -1 minus Y, which happens to be a 2, plus 2 times -2. Is that equal to -8? True or false? And the answer is it's true. And same thing for the third one. So you would do -1 plus 3 times 2 minus 4 times -2. And this happens to give you 15. If this is true, that is true. So that is an ordered pair or an ordered triple. It would only work if it works for all 3. So anytime you do any of these systems, if that would happen to have a 4th variable, it would have to work for all 4. Whatever the system is, it has to work. Is that fair enough? Easy enough for you to follow?
Yeah, seems simple.
Easy. So it has to work for all of them, and it does not work. It doesn't, no good. Okay, let me do the next example for you here. We have example 2. In example 2, we're also solving the system. They're giving us 3 equations. We have to find x, y, and z. So they give us 5x minus 2y minus 4z is equal to 3. We have 3x plus 3y plus 2z is equal to negative 3. And we have negative 2x plus 5y plus 3z, and that's equal to 3. So when we solve the system, I tend to like having a method. And my method is I use one of these as an anchor. Doesn't matter which one you choose, I just choose one. So let's say I choose this one as my anchor. Notice that I'm going to write this twice. I'm going to repeat the same equation here. All right, and now what I'm going to do is I'm going to place this equation over here. So this is my 3x plus 3y plus 2z equal to negative 3. I'm going to place that one there. And I'm going to take this one and I'm going to place this one over here. So that's my negative 2x plus 5y plus 3z equal to 3. And I'm going to decide at this point which variable I want to cancel. So whichever variable I decide to cancel, I'm going to stick to it for both. I'm going to go for the z. Let's cancel z. So now cancel, notice in my note, cancel z in both here and here. So for this one, I simply need to take this piece and multiply it by 2. That'll make this a positive 4z. Bye-bye z. Over here, I'm going to multiply this top equation by positive 3. This bottom equation by 4. Notice that I don't need to worry about the signs because it's already a minus plus situation, so that these are going to naturally cancel. Are you with me so far?
Yeah.
So I have 5x minus 2y minus 4z, focusing on canceling z, equals 3. I distribute that 3 all the way. This becomes 6x plus 6y plus 4z equals negative 6. As you can see, the z cancels. This leaves me now 11x plus 4y equals negative 3. Okay. I'm going to come over here. This is going to give me, since I decided to cancel the z. Did I miswrite that? No, I'm good. All right, so I have 15x minus 6y minus 12z equals 9. 4 times negative 2, negative 8x plus 20y plus 12z equals 12. Do you notice how my z's canceled? 15 minus 8x, that's going to give me, I got 7x plus 14y is equal to 21. Okay, now at this step, you see how I'm left with an x and a y, and here's an x and here's a y. So guess what I'm going to do? I'm going to combine these two. I have 11x plus 4y equals -3. I have 7x plus 14y equal to 21. Choose a variable and let's cancel it. Your choice. Let's cancel x. So I'll multiply the whole top by -7. I'll multiply the whole bottom by just 11. That becomes -77x minus 28y equals +21. The bottom one is going to become +77x. This is going to become 154y. And this is equal to 231. All I did was distribute. Notice that that cancels, the x's out. Okay, I'm now left with 154 minus 28. That gives me 126y is equal to 252. If I divide by 126 on both sides, I get y is equal to 2. Okay, I could take that argument now here and let's solve for x. I have 11x plus 4 times 2 equals -3. So that means 11x plus 8 is equal to -3. Therefore, 11x is equal to -11. Therefore, x is equal to -1. So now I have x is -1, y is 2. Now we just need to solve for z. Go back here. Any one of those three would work, your choice. Let's go with 5 times -1 minus 2 times 2 minus 4 times z equals 3. That gives you -5 minus 4 minus 4z equals 3. So -9 minus 4z equal to 3. I'm going to add that 9 to both sides. And therefore -4z is equal to 12. And therefore z has to be equal to -3. So my ordered triplet, -1, 2, -3. Do you want to try one before we move on? Yeah, no, yeah?
I'm good.
Yeah? For real? All right.
I mean, yeah, it's just like making the anchor, like you said. I feel like that's a great way to go about this.
Yeah, it just keeps you organized.
Yeah, I mean, as long as you do that, you just follow steps. It's like 8-1, you know, as long as you just do that.
Follow the steps. And there are many other ways you can approach this. I just like this method. Okay, example 3 is really more of the same. The only thing is with example 3 is you're missing a variable. Let me just briefly just talk about this for a minute. I don't necessarily have to cover the whole thing. But like in this one, when they give you the system, they give you a question that looks like this. And the spacing, you notice that there's no wide term here. Okay, they do give you the other ones. This is x plus y plus 2z equals 17. This is x plus 2y plus z equals 16. So they give you everything else except for that term. So guess what you're going to do? You're going to do plus 0y. That's all you got to do. Okay, and then do the same thing we've been doing. Nothing fancy. Now, number 4, I do want to cover with you because that is a different question. All right, if you're okay with this, you can solve for it if you wish. And
Professor, quick question. When you put in the 0y, do you add the z term or you multiply it?
oh no, you add it. So
You
it'll be
add it?
Unless I give you another sign in front of here.
Okay, cool. Thanks.
Let me see. In the question they give you here, they do not put anything in front of it, which means it's positive.
It means that you add them, right?
It means it means it's positive.
Okay, cool.
Now, this one I definitely want to cover with you, example 4. Did you have further questions on that? Do you want to work it out, or you understand what I'm getting at?
I mean, as long as you plug into 0y, it's just like example 2, right?
Exactly. Okay, example 4 is a little bit different. This is the modeling data part. And it's actually, it looks ominous, and it's probably just as easy. You just have to know what you're doing. So you remember these equations basically are y equals ax squared plus bx plus c. And so they're telling you this is the function we're going to focus on. They're telling you that you have a model of x and y values, where x represents the number of hours that you sleep. So I'm just going to put here sleep. And on the other side, you have death rate. I'm just going to be dramatic and put death. All right, so they give us three little numbers. They start with 4, 7, and 9. So this is like a person who sleeps 4 hours. This is a person who sleeps 7. And this is a person that sleeps 9. And based on these estimates, the predicted value, or the response variable, is 1,682. So if you sleep basically 4 hours, this is the number of people that tend to pass in millions. I'm sorry, per 100,000. Per 100,000. For number 7, you have 626 in 100,000. And here you have 967,000. They want you to solve for the model using XYZ. We want to solve for the coefficients that are missing, which are A, B, and C. Now, you notice we have X, so we have all the X values. And we have X here, so we're good. We just need to use that X to solve for A, B, and C. We know Y, the response variable for each, and that's part of our equation. So we'll just solve for A, B, and C once we're ready, which are the solutions of the system. So if I begin with this one, I'm going to start by saying that we have 1,682,000 deaths equal to A times 4 squared plus B times 4 plus C. And we're getting that from our table, if you recall. Go back to your table. Okay, if I do the 7, I would see in this case I have 626,000 deaths, where I have A times 7 squared plus B times 7 plus C. And my third equation, where I sleep 9 hours, which is the equivalent of, or results in 967,000 deaths, is equal to 8 times 9 squared plus B times 9 plus C. All right, now we simply need to collapse that. So this results, the first one is 1682. So we have 16A plus 4B plus C is equal to 1,682,000 deaths. My second equation, 49A plus 7B plus C is equal to 626,000 deaths. And 81A plus 9B plus C is equal to my 967,000 deaths. And now we solve for the system, just like we would normally. I'm going to give you the solutions, and I want you to take 10 minutes to see if you can arrive at these answers. And then we're going to do the next example, which is 4 variables. So the solution for A should be 104.5. The solution for B should be 1,501.5. And the solution for C should be 6,016. All right, you want to take a few minutes and see if you can solve that for yourselves. You should end up with the same answer I have here. And then,
Sorry, Professor, it's not negative 1,501.5, right?
yes, it is.
It is? Okay, cool.
I think Thumbelina has locked herself in a room by accident. Let's see. How's it going? Are you getting close to these answers?